So chapter 4 is about sound. Sound is a mechanical wave. So everything we studied about mechanical waves in chapter 3 is going to be used in here. Not only mechanical wave, but also longitudinal wave. Sound is a longitudinal wave. And we can start a longitudinal, we started a longitudinal wave by compression, remember. There was a spring, we were pumping the spring forward and backward. When we push it forward, it makes a compression. When we pull it back, it makes a stretch region. But this stretch region later named as rarefaction at the end of chapter 3, we named it as a rarefaction. As compression was the region of higher density or higher pressure than the normal, but stretch region was lower density or lower pressure than the normal. Now we will continue with the sound, because sound is also longitudinal wave. It also starts like a kind of compression when you are talking, when I was talking. So you are continuously producing compressions and rarefactions one after another. So a sound wave begins with a vibrating object, correct. My vocal was also vibrating when I was talking. When you keep it, hold your hand and you can feel it. So the device which is used for making sound experiments are called tuning fork, and this tuning fork has two arms called as prong. When it is vibrating, as you see here, or when you hit it, it starts to vibrate. While it's vibrating, it's producing longitudinal waves, which is going to be named as sound. And as this tuning fork is vibrating and the prong is swinging in one side, it causes air molecules to come closer, which tells you that it produces a region of higher density or higher pressure than the normal one. But when it's swinging back, this time opposite happens. When the prong is vibrating right and left, it produces a region of higher pressure and higher density than the normal. When it's swinging back, it produces a region of lower density and lower pressure than the normal. And this higher pressure or higher density than normal is known as compression, or lower pressure and lower density than the normal is called as rarefaction. And as this tuning fork is vibrating, continuously compressions and rarefactions are released one after another. This tuning fork swings with simple harmonic motion because it's an elastic object. Even though we don't see vibration to be visible, we make it visible by inserting a glass of water, remember. So when tuning fork vibrates with simple harmonic motion, of course, it's the source. Remember, we said that everything in contact with the source will vibrate with exactly the same frequency. Yani, if tuning fork vibrates with simple harmonic motion, the air molecules which are in contact with the tuning fork will also vibrate back and forth with simple harmonic motion. Tuning fork, because it's vibrating with simple harmonic motion, where any source which vibrates with simple harmonic motion produces a waveform, which is a sine wave. That's why this is a wave. This is a sine wave which defines how pressure and density is changing as waves from the tuning fork travels in air. As you see, some regions have compressions, which is the region of higher pressure and higher density. Some regions are rarefactions, which is called lower pressure and lower density. And compression, rarefaction, it goes on like this. Compressions, crest of the sine wave, rarefaction, trough of the sine wave, crest, trough, then it goes on like this. And this dashed line is representing normal atmospheric pressure, or we can also say it's like equilibrium position, because equilibrium position is the position of a medium before the vibration starts. So this is equilibrium position. After molecules of the air start to vibrate, this pressure is changing. Compression becomes higher, rarefaction becomes lower. And the crest of the sine curve corresponds to compression, and the region of higher pressure and density than the normal, and the trough of the sine curve corresponds to rarefaction, which is the region of lower pressure and density than the normal. And this graph defines how pressure and density of air changes as sound from the tuning fork travels in air. Be careful, this is only for the tuning fork. At the end of chapter 4, section 3, we also talk about that. Tuning fork vibrates with simple harmonic motion. Its waveform was a simple waveform. This is not my sound. My sound is not like this. Okay. Then let's continue. Audibility. How a sound is audible? By the time, what does audibility? Audibility means? Let's talk about this. Audibility is a sound to be able to heard by a human. It's called audible sound. If a human cannot detect a sound, this sound is not audible. And audibility depends on frequency. Yani, as a human, we can hear a sound, we can detect a sound at between two specific frequencies in a range. This is a range from 20 hertz until 20,000 hertz. And this range is the range for audible sound for human kind of human being. But there are some sounds which is not audible for us but audible for some animals like elephants, which is the sound whose frequency is less than 20 hertz, which is known as infrasonic sound waves. But by the time infrasonic sound waves are used by elephants, they use this to communicate. Why? Because we know that smallest frequency means longest. Yani these infrasonic sound waves, why not? Such a question. Which of the following sound waves has the longest wavelength? Infrasonic sound waves has the longest wavelength. When they have the longest wavelength, they can travel very long distance without reflection. We will define next slide that as the wavelength increases, the reflection of the sound decreases. Yeah, we don't say directly inverse proportion, but it's a fact, okay? As the wavelength gets shorter, sound starts to reflect easier compared to longer wavelength sounds. That's why these infrasonic sound waves can travel very long distance. That's why most people they are using this sound for communicating with their friends or families. Other sound waves which we cannot hear is the sound whose frequency is 20,000 hertz, known as ultrasonic sound waves. Bats and dogs can hear this sound, and also dolphins are also using ultrasonic sound waves to locate distant objects. So they send ultrasound pulses in the water. This sound, because they have very high frequency, so short wavelength, can easily reflect it from a fish back to the dolphin, and dolphin can understand the size, shape, distance, how fast it is moving, so then about this prey, and then go after it and then feed himself, or itself. Okay. Some marine animals such as dolphins use ultrasound waves to locate distant object, which is called as echolocation. Why is it called echolocation? Echo means reflection of the sound. From this reflected sound from the fish, dolphin gets information about this fish. We are using this in medicine for ultrasound imaging, and also especially for speed, measuring speed, high speed of a car. This technique is used. Echolocation. Yani echo is the reflected sound, reflected wave from a wall or an object. So when the sound is reflected from a wall or an object, it comes back. From this information from this common reflected sound, we gather information, which is called echolocation. Okay, and speed of the sound wave. First, sound wave is a mechanical wave, we know that. Mechanical wave speed depends on medium. Medium determines that. Yes. Yani, sound, if you want sound speed to be changing, so you should make it move from one medium to another. One fact is this. Second one is property, yani temperature. So one of them is a second medium. Now, this table shows you how speed of the sound is in different media, like gas, liquid, and solid. As you see, gas is 346, air. And the liquid seawater, 1,530, but copper or iron, 5,000. Yani, as you see, as medium is changing, speed of the sound, not only sound, any mechanical wave is changing from medium to medium. Then we can see that in which one speed is the highest, the fastest. Solid sound, not only sound, any mechanical wave is the fastest in solids, slower in liquid, slowest in gases. Why so? Because in solids, molecules are closest. And we know wave is a transfer of vibration. If they're so close to each other, easily or quickly, vibration is transferred from one particle to the next one in solids. But in liquids, they're close, but not as close as the solids. It is still faster, but not as fast as the gases. But in gases, no, they're not that close. So a particle must get into contact with another one to transfer the vibration. The vibration takes time. From one particle to the next one, it takes time, which makes vibration or disturbance to travel slowest in gases. One factor is this, absolutely, the medium. As medium changes, speed of sound, speed of any mechanical wave changes. And maybe better to know this in here, as sound travels from air to water, speed increases, but frequency unchanged. For air, chapter 3. For a traveling wave, frequency is unchanged. It doesn't matter from where to where it moves. Then, according to this equation, look at this equation. If, we know V is equal to lambda times F from chapter 3. For a traveling wave, V is unchanged. Yani, as the sound travels from air to water, F doesn't change. But I know that it moves faster in water than air. If speed gets faster, what does it mean? This is unchanged. Wavelength gets longer. Yani, as a sound wave travels from air to water, speed increases, so wavelength must increase because F is unchanged. Yes?
Frequency depends on what?
Depends on the source. Only the source. After you make a wave, after you make a wave traveling, you can never change its frequency. How? You can make a wave of small frequency, big frequency, depending on the source. After that, when you do it, no more chance to change its frequency. Yes?
So frequency does not depend on the medium?
No, it's not. Just the source. Only the source. When the sound travels from air to water, because F is unchanged, but speed changes, wavelength must change. Greater speed, longer wavelength. Smaller speed, shorter wavelength, as the sound travels from one medium to another. But medium one factor, which affects the speed of a mechanical wave, so does the sound. But there was one more factor, property of the medium, especially in medium, the temperature, especially in gases. So, speed of sound in gases changes with temperature. Why? Because as temperature increases in chemistry, you know that. Remember, if you want to transfer the vibration from one particle to another, there must be a contact between them. During this contact, vibration is transferred. So, if you increase the temperature, this particle starts moving faster. Remember, kinetic energy of the particles increases. When they get faster, what's going to happen? They will get in contact more frequently, which tells you that vibration is transferred quicker compared to cold gases. In hot gases, faster. In cold gases, slower. This is a table about how air temperature affects the speed of the sound in air. As temperature is 0 degrees Celsius, in air, speed of sound is 331. As 25 degrees Celsius, 346. Ne demiştik? Basra. 100 degrees Celsius, it is 366. As temperature increases, what's happening? So the speed of the sound in the air increases in winter. Now it's winter, 8 degrees Celsius in the morning. But in summer, 45 degrees Celsius in summer morning. So the speed of the wave, sound, your sound is not the same. But don't get confused, we are not talking about the frequency. Sometimes you think that speed is related. No, speed is not related to frequency. Frequency just depends on the source. Okay. And also pitch later we will define, but it's about relative motion, nothing else. Okay. Then, one more thing. In gases, temperature causes a big change in the speed. But in liquid and solids, temperature cannot produce so noticeable change in the speed of sound. Why so? Because the molecules of the solids and liquids are already close. Increasing their temperature does not make a so big difference in the speed of the transfer in the vibration. Why? Because they are already close, they can pick up the vibration from their neighbors so quickly. So that's why I say that this difference in speed due to the temperature change is less noticeable in solids and gases, solids and liquid, more noticeable in gases. This is important. Then, sound waves propagate in all directions. When I was talking right now, not only these students, also you hear me. Not only you, they hear me. So everybody hears me when I was talking. In which direction I'm talking doesn't matter, because my sound is traveling in all directions, so it makes a sphere. Why does it make sphere? Because this disturbance from my mouth travels to the right, left, up, down with the same speed. Same medium. Then it makes a perfect sphere around my body, around my mouth. So that's why we say that sound waves are approximately spherical. But we are not going to draw spheres, we will draw circles instead of spheres like this. These circles are representing the compressions which produced by a tuning fork. Of course, as when I was talking, wavelength is not the same always, because sometimes I am increasing my frequency, sometimes decreasing my frequency. But tuning fork, it has some specific frequency, certain wavelength. This is the waves produced by a tuning fork. Even though I put here a loudspeaker, it's not. Okay, tuning fork. It produces compressions, several compressions one after another, and between two compressions, of course, there is rarefaction. I represent them by dashed line rarefaction. Compressions are blue circles. So compression, higher pressure, higher density than the normal. Rarefaction, lower pressure, lower density than the normal. And these compressions given a new name in this chapter, which is wave front. Compression is wave front. And from compression to compression, we knew that it was 1 lambda. Again, from wave front to another wave front, it is 1 lambda. Okay. And a wave front, compression corresponds to the crest of the waves, pressure wave or the density wave. Rarefaction corresponds to the trough of this pressure wave or density wave. We noticed before. And one more thing, these red lines radial outward from the source is called rays. What do they define? They define the direction of the sound wave at this point, in which direction sound is moving. Is it moving to the right? Is it moving to the left? Or is it moving this way? Which way is the sound is traveling? Third way. Ray determines the direction of the sound wave at that point. For example, if I want to find what is the direction of the sound at this point, first I have to draw a ray from source, radial outward. I'm going to draw a ray. In which direction the ray is, in that direction is the sound travels. Yes?
Teacher, you said the frequency does not, it's like depend on the source.
Depends on source, what do you mean?
Yes, and lambda and V, since frequencies depend on source, if we change the medium, lambda is going to change.
Exactly.
The wavelength change.
Yeah, the wavelength can be changed by frequency and also by the speed.
It will also
Yes,
change
all
the
of them.
frequency.
Alright, then. Several compressions coming from a tuning fork. Separation between the compressions are 1 lambda, or between wavefronts are 1 lambda. This is the definition in your book, better to know. Wavefronts of a small portion of a spherical wave that is many wavelengths away from a source are nearly parallel planes. What does it mean? Look at that. It's a small portion. You are not going to take the whole wavefront, a small portion of the wavefront, like this, like this, like this, like this small portion. This small portion is for a wavefront which is many wavelengths away, almost a plane wave. What does it mean? Look at that. When it is close to the source, it seems to be a curve. But as distance from the source increases in terms of wavelength, this curve starts to approach a straight line. 3 lambda away, much closer. 4 lambda away, closer. So finally, of course, it's going to be closest to a straight line. Straight line in two dimension. In two dimension, it's a plane wave. Plane. You know, flat surface, like a flat surface. A kind of flat surface it happens. So, as the wave moves away from the source, a small portion of this spherical wavefront can be treated as a plane wave. But what is the condition for this? The point or the wave, this portion must be many wavelengths away from the source. This is the condition. Yani outermost. This is one of the sectional questions. Not innermost. Innermost cannot be treated as a plane wave, but a small portion of outermost wavefront can be treated as a plane wave. And breaking sound barrier. So we are not breaking anything by this title. In fact, we are making a sound source traveling faster than speed of sound. This is what breaking sound barrier is. But this can happen only if the sound source is attached to an airplane. Got it? No car has a speed faster than speed of sound. That's why we can talk only for airplanes, but not all airplanes, especially warplanes. This can happen. So this is a stationary airplane. When it's at rest, so it makes, say that its engine is on, it produces compressions in all directions. Left, front, right, back, left. Separation between the wavefronts in all directions, same. Which means wavelength on the right, wavelength on the left, wavelength in front, wavelength at the left, at the back. All are the same. Yeah, if there are observers on the right, on the left, in front, at the back, all these observers will hear the same sound because lambda is the same. But if this airplane lift off and start to fly some speed, but speed of the airplane is going to be less than speed of sound. This time, these wavefronts in front of the airplane gets closer. Remember the simulation I think I showed you? This is the simulation? Yes. So, normally the airplane was in here when this one is released. Then second compression is released when the airplane is closer to the wavefront in front of the airplane. So this makes that separation between the wavefronts are closer in front, but farther at the back. So in here, shorter wavelength, in here, longer wavelength. So they can give this picture to you, or put a source. In which direction the source is moving now? It's moving to the right. So in which direction the wavefronts are closer, yani wavelength is shorter, the source is moving in that direction. Okay, so this airplane is flying to the right. In here, wavelength, let me say lambda, and in here, wavelength, let's say lambda 1 or lambda 2, they are not equal. Yani, if there's a bird listening the airplane sound, in here another bird listening the airplane sound, they don't detect the same, we will define later, pitch. Pitches are different. But our case is not this, in fact. What if this airplane flies at a speed exactly the same as speed of sound? What's going to happen? This is going to happen. What is this? How this happens? Look at this relation. So this airplane releases a compression. Then compression will start expanding with speed of sound, but airplanes also flying with speed of sound. Yani, this portion of the wavelength airplane are moving together. They are moving together because their speeds are the same. Then it happens like this. It releases one more wavefront. So then what happened? In front of the airplane, these wavefronts coincide, overlap, meet each other. This is their compression. Compression is the crest of the density wave. Yani in here there are double crests. But there is no only two compressions meet. Several billions of compressions meet each other. Double crest, triple crest, 4, 5, 6, 7, 8, 9. So what happens in here? They constructively interfere. Right here, in front of the airplane, right there. These wavefronts constructively interfere. So if constructed interval, what happens in amplitude? Amplitude increases. So what is the amplitude determined for a wave? It's power. It's energy. It's square of the amplitude for a mechanical wave, remember. So right here produces a very powerful, more energetic sound, greater amplitude sound. This sound produced in front of the airplane is called as shock wave. Yeah, when the airplane attains the speed of sound, disturbance accumulates in front of the airplane that increases the amplitude of the resultant wave and creates a shock wave. Then if I ask you, which of the following cases shock wave is produced? A, when airplane is at rest. B, when airplane is flying at a speed less than speed of sound. C, if an airplane flies at a speed which is equal to speed of sound. So C is correct answer. Still we didn't break the sound barrier. Now we will break it. If you make this airplane faster than speed of sound, this time we are going to observe a phenomenon known as breaking sound barrier. So now what's happening in solution, we will see that. This airplane releases a compression. The compression is traveling, but airplane is flying faster than its own compression. Yani when airplane is in here, it releases compression. Later airplane goes in front of the compression, release one more. This is happening like that. I thought, but it must be in front. Airplane must be in front of this big compression. So what happened in this case? These compressions again meet each other, overlap, but not in front, at the edge. Because two-dimensional, we only show you left and right end, but this happens around the airplane everywhere. It's a conic shape, like that. Look at that. In here, in here, in here, in here, in here. All the compressions accumulate. In here, they accumulate. In two dimensions, like two crossed lines, but in two dimensions, it makes a conic shape. You just remember the conic shapes when we watched the video in the lesson. These conic shapes are in fact representing the shock wave, the fork which forms around the. But why is it called breaking the sound barrier? Because these shock waves are not traveling to the right; they are traveling towards the ground. Look at that. They travel towards the ground. If somebody stayed on the ground, and then these shock waves will arrive this person, as soon as it arrives a person, you are going to hear this shock wave as a big explosion. But this shock wave is not heard by only this person, everyone on the ground will hear these shock waves one by one. This is what happened in 2006 in Istanbul. When the airplanes, they made flight at the speed greater than speed of sound over Istanbul, everybody thought that they are bombing the city. Because they all heard the shock waves. They bombed some place, maybe. There's just sound heard by the people right there. Not the other part of the city can hear that. But shock waves are not like this. Everyone in the state will hear the shock waves. Yes?
Teacher, in here also when the speed is greater than the airplane also,
Yes.
shock wave.
Of course. They form at the edge. At the edge, yes. Not in front.
In one, two places. It's
Yes. So when speed of the plane exceeds speed of the sound, the shock wave will form at the edge of the plane and superpose. Superpose means superposition. Got it? Overlap. And give a huge explosion like bomb is released, dropped at that point. So, when this phenomenon is named as breaking sound barrier, yani if an airplane flies at speed greater than speed of sound, shock wave form at the edge and arrives to the ground. This phenomenon is known as breaking sound barrier. Okay. Then pitch. What is pitch? First, pitch is how high or low you can detect a sound. It's called pitch. But this high and low is not the same meaning in our daily language. Daily language, high and low sound, we generally use the volume. But in physics, the high and low sound is not about that. It's about frequency. How high or low frequency you are going to detect a sound is called pitch. Absolutely, pitch depends on source. Yani if the source frequency increases, the frequency detected by your ear also will, yani pitch will increase. One factor is this. They are directly proportional. Second factor which affects the pitch is the relative motion between the source and observer, which is called Doppler effect. So, what is Doppler effect? So, whenever a source is approaching to an observer, the pitch changes because we know that separation between the wavefronts in front of the sources gets closer, at the back gets farther. Now, this woman right here, because she's in a region where the wavefronts are shorter, will detect a smaller wavelength but higher frequency, higher pitch, we say that. And if the sound source and listener are relatively approaching each other, the listener and observer perceives a greater pitch, higher pitch. In fact, pitch, you can also think like this. To hear a sound, the sound must arrive to your eardrum. It must vibrate your eardrum. When the wavefronts get closer, the sound arriving to your ear is vibrating your eardrum more frequently. Because one of them comes, next other comes, next coming. So frequently they are vibrating your eardrum, so you hear a high pitch. So where wavefronts get closer, the wavelength decreases and frequency of the pitch increases. But when this ambulance passed by the woman, this time opposite happens. Separation between wavefronts gets. That's why your eardrum will detect vibration like this. But in here, it was your eardrum vibrating like this, but now it vibrates like that. So which makes you detect the sound lower pitch, lower frequency. Okay, if the sound source and listener are relatively move away, listener or observer perceives a smaller frequency, which is called as lower pitch. Wavefronts gets farther, wavelength increases, and frequency of the pitch decreases. Then, but how can we calculate the difference or this frequency by an equation? This is the equation. But then better to know this also. Right here, original frequency is F. Let me show it. This F. Original wavelength is lambda. In here, pitch frequency is F prime by the woman, and wavelength is lambda prime. So which one is, compare F and F prime. Which one is greater? F prime is greater than, F is less than F prime. Higher pitch, this is going to be higher than the original frequency. What about wavelengths? Lambda and lambda prime. It's going to be opposite. Inversely proportional. Yani wavelength gets shorter, but frequency gets higher in the case of approaching. Yes?
Teacher, if a man is in the ambulance, the driver...
For driver, nothing changes.
Nothing?
No. Relative motion is the key word. Yani the source and observer must relatively approach or relatively move away. For the passengers inside the ambulance or train or airplane, nothing changes for that. Okay, for this one, original frequency is F, original wavelength is lambda. Woman pitch frequency F prime, wavelength is lambda prime. So, this time lambda prime is lower than lambda. What about frequency? Opposite. F prime is less than F for this case. Then how can we calculate the pitch frequency, detected frequency, by this equation? What is this equation? Pitch frequency is F prime. Original frequency is F. There is V in numerator and denominator known as speed of sound in air. VO, observer speed, V as source speed, and your equation of course is 1 plus minus in numerator, the other one is denominator. Only thing you need to determine in here is that, what is this sign? Positive or negative? The rest of them is the equation. Now I'm going to show you quickly how to do that by this problem. A parked ambulance, ambulance is the source because it emits the sound. Source. Park means sources at rest, 0. Emits a sound of frequency, original frequency, F. What frequency detected? Frequency detected is known as F prime. By an observer moving. Observer is moving. With a velocity, VO, 20 meters per second. A. Towards the ambulance, approaching case. What happens to the pitch? Increases. F prime is going to be greater than F absolute. Away from the ambulance, approaching, opposite of moving away cases. F prime is less than F. Find them one by one. Okay. So I'm going to apply this equation. F prime is equal to F V plus minus VO divided by V plus minus Vs. First, one of them is 0. Which one is 0? Source is 0. So I don't need to worry about denominator. Because the negative is okay, it's 0. We care only numerator. Now then go with A. And then go with choice B. Choice A. F prime is greater than F. I should make F prime greater. So numerator must be a big number. Big number is provided by, not subtraction, by addition. That's why F prime will be calculated F V plus VO divided by V. Then you are going to insert the numbers and you will find it. I'm not going to calculate, but you can find it very easily. But for B, moving away cases, what should happen? F prime must be less than F. To do that, numerator must be smaller. To make it smaller, we should subtract them. For B cases, F prime is going to be F times V minus VO divided by V. And the rest of them, you are going to use your calculator and you'll find the answer.